So we can apply the angle criteria, which says that the sum of the zero angles minus the sum of the pole angles is equal to 360 degrees. It's 360 this time as opposed to 180. And we can do this now by going back to this diagram here and guessing this point here. So it would be advantageous now, I think, to just quickly redraw this. So we'll rub out some of this stuff here. Like that. That's probably okay. Re-establish this line. And that line. So what we're going to do next is, remember the way the method works is we guess now a point along here. So we could guess, an inspired guess might be somewhere about there. And then what we do is we draw straight lines from the poles and zeros to that point. So we draw a line in here. Then we'll draw a line in here. Then a line in there. And one there. And finally one here. So we've drawn now some lines from our guess point. This is a guess point, this one is a guess. And we draw lines from that point to all the poles and zeros. We then start to measure the angles. So this is a 0, so we're going to call that, say, alpha 1. And this is a pole, so we call that one beta 1. There's another pole here, beta 2. And another pole here, so that'll be beta 3. And finally that angle there will be beta 4. Now we can use a protractor to measure these. This is one I've specially made, but I'm not going to use it because it's not accurate. We could put our protractor there and we could measure this angle. It's about, say, let's say it could be 70, 110, so it's actually going to be 110 to measure the different angles. And so we could then put them into the equation, which gives us alpha 1 minus beta 1 plus beta 2 plus beta 3 plus beta 4 will equal to either 0, could be 0 or 360. It depends on how you measure the angles, but this is not going to be 180 this time. I would suspect in this particular case that what's going to happen is going to go to 0, because you can see that angle there is probably equal to the sum of those. So it's probably going to go to 0 in this particular case. If it does come to 0, then you know this point is on the root loci and you found the point. Now if you did this, the actual point itself is at 3.8. So if you did this by hand correctly, it's at 3.8J. So having got that far now, we can then go on to use the magnitude criteria to work out the gain at the point. So go back to this one, let's just rub this up quickly. So we can now apply the magnitude criteria. And this one says that the gain, Kp, times, if we've got a number along here, we'd have put the number in as well, but we've just got a 1, so it's a 1. And it'll be the product of the zero distances divided by the product of the pole distances is equal to 1. This rule now is unaffected whether it's a positive or negative 0. It doesn't matter. So we'll get to the expression now, Kp. And now what we'll have to do is go and measure now. My ruler unfortunately hasn't got any scales on, so I can't use it. But if it did, I could. I could now measure from there to there. And we'll call that, say, because it's a 0, we'll call it M1 hat. I could then measure from there to there, call that one, say, M1, measure from there to there, call that one M2, that one could be M3, and finally that one could be M4. So we've measured M1, M2, M3, M4, and M1 hat, and we can now stick them into this. So it'll be Kp times M1 hat over M1, M2, M3, M4 is equal to 1. And in this expression now, we know everything except for Kp. So we can solve that for Kp, and the Kp then would be the value of the gain here at which the system, the root loci, went from being stable to unstable. Now there's one last thing that might want also to consider. Rather than going up and down the imaginary axis, we could go up a constant damping ratio line as an alternative problem to solve. So it's worth considering that one as well. It's exactly the same technique as the one we've used here. The only difference is now, rather than going up and down this line here, we now go up and down a line, a constant damping ratio line. And so let's have a quick look at that one. So I'll just put some new axes on. So that, it's not so good, but not too bad. There's our axes, and we can put our stuff back on again. So we've got a pole at -4, -8, -10, -15, at 0, at 1. And this time what we do is we now solve an equation where cos theta is equal to the damping ratio to get an angle theta. Now in this particular example, I've decided to choose theta, or the damping ratio, equal to 0.6. So cos of theta turns out to be 53 degrees. You can solve that one on your calculator. And then what we do is we go back to our diagram and we draw a line here now, like that, such that this angle here, theta, is 53 degrees. And this line now is a constant damping ratio line. And we can now find a point on that line. So we could guess now, some of the guess methods, you guess a point here. So you guess the point, and then what we do is we then go back to our diagram and we draw straight lines now from all the poles to the zeros. We'll draw from the point, so draw a line in there, draw a line in there, draw a line there, there, and there. So the method is quite similar to what we did before. Then bring out a little protractor and start to measure angles. So get this one here, measure that one as alpha 1. Then measure this one as beta 1. Then measure that one as beta 2, and that one as beta 3, and finally that one as beta 4. Then we could go back to our angle criteria. What to do here? So the angle criteria is that the sum of the zero angles minus the sum of the pole angles is equal to 0. So we're going to go for the 0 solution as opposed to we could go for 360 or 0, but not 180. So this will give us now that alpha 1 minus beta 1 plus beta 2 plus beta 3 plus beta 4 should come to 0. So you can see, I'm looking at the diagram, there's a fair chance that alpha 1 will equal to the sum of the betas, and it'll go to 0. That's if you choose the point correctly. If it doesn't act correctly, move it up and down until it does come out correctly. Then once you've got it correctly, you can then move on to your magnitude criteria. So it's exactly the same now. We go back to the diagram, take our ruler, which could have some sort of scales on, and start to measure the distances. So you can measure that distance there as M1 hat, this one here as M1, second one as M2, third one as M3, and final last one as M4. So we measure from there to there, there to there, there to there, there to there, there to there. And we get the values for M1 hat, M1, M2, M3, M4, and again put them back into this equation here. And that will then give us the value of Kp that puts us there. So this is a little lecture on how to plot root loci for non-minimum phase systems, and also how to compute using the angle and magnitude criteria the gain, either which it crosses the imaginary axis or when it has a certain value for the damping ratio. So I hope you found that useful. Thanks.